I don't know if it's starting. Oh, there we are. Okay. We're all here. Okay. First day. Isn't that a great graphic? Found that online. Made that myself. No, I didn't make it myself. You steal everything online. That's the best part about it. You know, teaching is so easy today. It's so easy. I mean, when I first started, we didn't have computers. You didn't use computers. You didn't even use computers for grades or anything. You never used a computer. You just had to write on a blackboard. Can you imagine that? And I rode my horse and buggy to school every day. And that wasn't that bad, but it was a long time ago. But yeah, you know, I'm gonna have a lot of graphics like this, I guess, throughout the year. That usually do something more than just, you know, Rube Goldberg type device. You know what a Rube Goldberg device is? You should. But anyway, it doesn't really matter. It's not important. All right, let's get some notes here. Let's talking about chemistry, because that's, after all, what the title, or what this chapter, what the course is called. Okay, and the first chapter, chapters 1 and 3, is on matter and energy. I'm going to give you, as disorganized as I often appear when I'm walking around and doing things and even doing demonstrations, your notes are not going to be that way. Your notes are actually going to be very organized. I'm going to have them organized that way. I find that, you know, helps you to think, helps you to get, you know, do well on the test if you can see where everything fits together. So I try to give it that way, but I also try to keep it, you know, with the questions I'm going to ask you, I'm going to try to make them more open-ended and thinking kind of questions. Well, let's start off with, what is chemistry? Okay. That's the title of the chapter. I'm title of the class. Why am I here? We already talked about why you're here. We already talked about how, you know, most of you don't need chemistry. Most of you are never going to need it. You're not going to be chemistry majors, and even the ones that do need it, that's quite a few of you who will need it for healthcare, whatever health field. You know, it's not going to be the major part of your studies. So, you know, I'm going to try to do something along the way that's different than just teaching you chemistry. All right, so first of all, let's start with a simple definition of chemistry. All right, what is chemistry? Well, if you look at the book, it says it's the study of the structure, properties, and reactions of matter. The structure, properties, and reactions of matter. Okay. Where'd it go? I can't copy it now. It's not there anymore. Lesson number 1, how to take notes. What's her name? I don't even know your name. I don't have anybody's name. Kirsten, did you get it all down? She's good. Most of you got about 3 words down, because here's how you were writing. Here's how you were taking those notes. Don't put your pencils down. Put your pencils down. Put the cannoli down. All right. There it is. Here's how. Don't write. Here's how most of you took those notes. I was watching. The study of. You bobbed your heads up like 18 times for 9 words. Now, I want you to think about this. I've said that definition. You can go back and watch it tonight. I said it twice. It was on the board for, you know, maybe 10 seconds. Most of you did not get it copied down. How bad is that? Let me see if we could do an experiment with another sentence. Can you just repeat the sentence I just said? Somebody can repeat that.
Let's see if we can do this one.
Say it all out. Yeah. So you can repeat that sentence, right? And it had no more words than this one had. Lesson number 1, how to take notes. Your college professors are going to talk much faster than I do, and I talk pretty fast. All right, first lesson is you don't bob your heads up and down and write every word. You read the whole thing. You listen to what he says, and then you write the whole thing down. Now, I'm not going to be erasing every time this to prove my point, but you will do 2 things for you. Number 1, you'll actually get something out of it if you're listening and to him or her, and you listen to the entire thing. You're not getting anything out of copying these white letters onto your paper. You're getting nothing out of copying the word the, copying the word study, copying the word. You're getting nothing out of that. But if you listen to the whole thing and his explanation, and then copy it down all together, it will make a little bit more sense. You'll also, number 2, write it faster. Think about how much time you're wasting bobbing your head up and down. And finally, number 3, even though I said there was 2. 3, don't worry about neatness. I'm not collecting homework. I'm not collecting notebooks. Do not worry about neatness. Write as fast and as sloppy as you can. because you're going to have to learn how to do that. You're going to have professors who are not speaking English for two reasons. One, they're probably from a foreign country. If you go to a large university, seriously, if you go to a large university, you're taking a science class, odds are you're not going to get an American-born, English-speaking, first language English-speaking professor. You're going to get a lot of foreign professors. So you're going to have a hard time listening to these people talk. I just got out of a class like that this summer, all right? And it's difficult because not only, I said foreign language in two ways. There's literally, they're from a foreign country. And secondly, science is a foreign language for you, right? So you got two foreign languages you're learning at the same time. You better listen first, then worry about copying the actual words down. All right, you have to learn how to take notes. All right, write that down if you haven't already, and do write fast, write sloppy. That has 2 points too. The faster you write, the more you can listen to the explanation I'm going to give or somebody else is going to give. And the sloppier you write, the less chance someone will ask you to borrow their notebook to copy the notes down. That's a great thing. You don't have to worry about that. So it's a selfish thing too, but that's all right. All right. So that was my lesson number 1 was taking notes. Here's lesson number 2. That's garbage. That means nothing. I'm not going to ask you crap like that. That's the kind of junk you have to do in biology. What's the definition of Golgi body? What's the definition of mitochondria? What's the definition of this, that, and the other thing? All right? And then you spit it back on the test and you get an A. And most of you are very good at that. You wouldn't be in this class. All right? You'd be very good at that stuff. Okay? That's not the you're never going to see that. I put that on here as an example of what you won't see. I am not going to teach that way. I'm not going to teach by giving you a bunch of unrelated definitions and saying, memorize these and then spit them back to me on a test. Now you might say to yourself, well, that's good. But then you might think for a second, wait, maybe that's not so good because I'm really good at memorization. How many of you guys are really good at like, oh yeah, I can remember in your notes what corner it was in and what side of the notes it was on. You know, you're very good at that. And that served you well over your careers, over for the last like 16 years. You guys have done really well with that. So me saying that I'm not going to make you memorize all this stuff may sound appealing at first. Then you're going to realize, well, what are we going to do? Well, I'm going to give you concepts, and I'm going to ask you to apply them and explain them and do math problems with them. That's what's going to make this class more difficult, probably, for some of you. Because some of you, and I've had some number 1s, 2s, 3s in the class who were incredible memorizers, but couldn't think their way out of a paper bag. I mean, they could not think and explain, and you give them anything out of what was specifically in the notes, and they would struggle with it because they just couldn't see it. All right, and you're gonna, and by the way, you're all gonna be like that because it's just you're gonna have to struggle with it, but you'll get better. Same as I just said about the exercise. You know, you don't just go out and play basketball. I don't have to practice. You know, I don't have to study. I don't have to practice. I'm just gonna go out and play really good in the game day. It doesn't happen that way. You've got to do this kind of work, all right? And it's not going to be easy at first. It's not easy running those sprints, and it's not easy lifting those weights. But if you do that hard work, all of a sudden it gets easier in the game day, which game day is test day, or game day is college, or game day is life, whatever. All right. So this is not something you're going to get on a test. You ain't getting this question on a test. You're not getting a definition of chemistry on the test. I want to know what's more useful about chemistry. I want to talk about, for example, the scientific method. This is something you will get on the test. And not just memorizing the steps of the scientific method, not just that, but rather applying that knowledge in the sense of, number 1, we'll be doing about 27 labs this year, and we'll be applying it there. First lab we do, we'll be applying it. Today's demo, we're going to be applying it. You're going to be doing that. All right. But also number 2, on the test, obviously I can't have time doing that on a test day. So what am I going to do on a test? I'll give you a scenario. I'll give you a sentence. And I'll say, was this which one of the steps in the scientific method was this? And I'll have a specific thing that happened. And then you'll have to apply it. So it's not going to be a matter of memorize and spit back to me these 4 steps. It's going to be telling me which one of these statements fits into that step. So you see the difference. It's not going to be just memorization. Now, let's see how much you do remember about the scientific method. Okay? Does anybody remember what the first step of the scientific method was? What was it? Somebody's got to remember this. Come on. Come on, somebody remembers it. Raise your hand. I'm going to call on you if you don't raise your hand. Don't make me call on you. Don't make me cripple you. I'll give you a reason to cry. All right, that's it. Too late. Too late. I know somebody out there knows this. Give me. You've all heard of it. You've all gotten the scientific method probably in every science class you've had. By the way, I guess this kind of proves my point, doesn't it? If you really can't remember it, how useful was it to memorize that? How useful is it if you can't give me the definition of mitochondria right now, or endoplasmic reticulum? How useful was it for you to do that during that class? That's my point. But I think you should remember having said it so many times. So let's just randomly, I don't even know where you are. Kylie, where's Kylie? Kylie's right there. Oh my God, that's so funny. I had no idea it was Kylie. Kylie's right in front of here. Kylie, give me a step of this. I don't even care if it's the right one, the first one.
Have a theory.
That is a step, but that's not the first one. That is not the first one. What's the first thing a scientist is going to do? Observe. Yeah, observations, absolutely. By the way, I forgot to give you the definition here. It's a set of general principles used by scientists to study the world. So it's a way of looking at things. It's a way a scientists look at the world. Set of general principles used by scientists to study the world. Again, you're doing it again. I see the heads bobbing. A set of general principles used by scientists to study the world. I can remember it without having written it down, without having it up there. You can do it too. Listen to the whole thing. It's a way that scientists look at the world. It's a different way than a plumber looks at this pipe. I look at this pipe, a scientist looks at this pipe here, and he sees that it's shiny. Metals are shiny. We know that. They have luster, right? It's bent. It's malleable. I could bend it. All right, it conducts. If I turn it on, I can tell if it's hot or cold water because right away it conducts heat or it also conducts electricity through it. All right, but a plumber doesn't look at it that way. He looks at it a different way. So what are the general sets of principles that we're going to use to look at things in science? And by the way, in my opinion, I could spend all day on this because it's one of the things that we have totally lost. All right, and I'm going to get when I get to the end of this, as a pop science. The stuff that you think you know is science has totally lost this ability to look at things from a scientific perspective. They've also gone further and beyond what science was meant to do. And I'll try to explain that as well. But let's start with the first one. You said observation, and you're right. Observation is the very first thing that scientists do. They look at things. All right? I'm going to pass around, all right, after I go over these. Maybe I'll do it before. What do you think? Should I do it before or after? I'm going to pass around, there's like 5 different black boxes, I'm going to call them. They're actually old film canisters. No one uses film anymore. Pass these around, and I want you guys to tell me what's in them without opening them up, obviously. And we'll see what you guys get for your answers. All right? But maybe I'll go over it, since I got the camera rolling here, I'll go over the steps first, and then I'll see if you guys can come up with the answers to those and show me how you applied it. So let's go over the steps first. First thing a scientist does is going to observe. And those observations are usually based on measurements, and we call those things data. Okay? So I don't just look, I mean, sometimes you do just look, I wonder why the ocean's blue. I wonder why the sun's hot. You know, I mean, that could be an observation right there. Now, look, the sun's hot. The sun's bright. So you observe things. And when you see these things, you're going to observe some stuff there, but you're going to be limited in your observations. Okay? Now, after I observe a few things, I start to get a question about it. What do we call that question? You know this word, it's a biggie. What's that guess that we think is going on here? You all know it, come on. Hypothesis, sure. You get a hypothesis. So I think, hey, I noticed, you know, fire is hot. I wonder, you know, notice this thing is hot, and I wonder what's going on. Maybe it's what kind of reaction's going on there. So you notice your hypothesis is basically a testable interpretation of the observations. It's an educated guess. That's probably what you've been taught before. The word is educated, like the phrase you might have heard was educated guess. And it is an educated guess. But it's not just any old educated guess. I can't just say, well, I think the universe, at the end of the universe, there's a big smiley face. All right, because I can't test that. All right, I have to have a testable observation. I have to have something I can test. That's something that we've completely lost a lot of times in the debates going on today with a lot of modern science. We kind of ignore the tests and the testability part. Physics has become that way. Physics, theoretical physics is kind of crazy. You guys, how many of you are in physics in this class? You won't get into this until you get to college, maybe not even then. But a lot of string theory and all this other crazy stuff they talk about in physics, it's just theory. I mean, there's no way to test it. And that's one of those things I'm talking about, how the scientific method has been ignored. I mean, there's all kinds of crazy ideas about the fundamental building blocks of matter at the physics level. I'm going to give you, I'm going to stop way above that, with atoms. But the fundamental particles of the universe, nobody really has a way to test this. They just come up with all these crazy theories and they can't test them. And that's kind of tough to call that science after a while. And you don't really know a lot of what I'm talking about here, but trust me, if you read more pop science, you'd realize that. It's almost like people are throwing theories out like crazy. When Einstein came up with this theory of relativity, he gave some reasons to believe it. He gave some testable and falsifiable predictions that if they didn't happen, he would have been wrong. Well, nobody does that anymore. Nobody does that with, let's take another situation, like with global warming. Global warming includes everything. If it gets hotter, that's global warming. If it gets colder, that's global warming. If it gets rainier, that's global warming. If you have droughts, that's global warming. Well, that's ridiculous. That's not a testable hypothesis. You got to tell me what's going to happen next year, 10 years, 20 years, 30 years down the line. This is what's going to happen. And if you can't do that and test it and see what's going to happen, or if you ignore when the data doesn't fit your situation, it's not science. It's not science. There are, by the way, there are things about global warming that are absolutely correct, but there are also things, the predictions they make, which are crazy. And they're not testable either. Or when they are tested, they're falsified, and then they just ignore it anyway. All right? A theory that predicts everything, that answers everything, actually predicts nothing. If I tell you that this theory explains why it might get warmer, but it also might get colder, why it might get rainier, but it also might get droughts, what am I saying? I'm not saying it. How could I be wrong? Whatever happens proves me right. That's crazy. You can't do that. So it has to be a testable interpretation of the observations. Okay? An experiment is your next thing. That's what you want to do. And you're going to do not very much of an experiment in this case, of the little demo I'm going to do today. But of course, throughout the year with 30 labs, you're going to do a lot of experiments. And you know what an experiment is, I'm sure. It's a test that helps determine the validity of a hypothesis. Here's another big change from the way people look at science today versus how it really is. Okay? Here's another big change. The results of the experiment, now I want you to stop for a second. Don't write this down. I want you to just listen. The results of the experiment can support or falsify a hypothesis, but they can't prove it to be correct. That's another. How many times you've heard, well, that's a proven scientific fact. Global warming is a proven fact. Evolution is a proven fact. That's not science. You never prove anything, but don't write, never prove anything in science. You get data that either supports your hypothesis or it falsifies it. But you never get to the point where you say, okay, we are now at, facts are data. Data's not, you don't argue with data. There's data, there's data. There's like something weighs 4.8 grams. That's data. But to make a theory and to say that that theory is correct, no doubt about it, it's been proven true, just shows you how stupid we are. Because how many proven theories have been proven wrong in the past? The Earth is flat. The Earth is the center of the universe. That was the conventional wisdom, prevailing wisdom. How about you ever hear of plate tectonics? The Earth, right? That was considered a crazy theory. Scientists argued with that. Newton's laws, all thrown out the window when Einstein came around. Every one of those proven theories were proven wrong. You never prove. This is the most important thing you're going to see about pop science, that they don't do this anymore. People use this all the time. All right, copy that down. They use this all the time. They try to say that science has proven beyond a shadow of a doubt. The debate is over. All these things are proven. It's not what science does. That's kind of shocking. I see the looks on your faces. I know you're shocked by that. But I have such faith in science. Faith's the better word, because that's what you really have, faith. We have a faith in this class. Faith is a better word, because that's what you really have in science if you really believe that the scientific theories of today will never be proven wrong. Now you say, well, you just used the word proven. I can prove something wrong. I cannot, in science, prove it correct. I can only get mounds and mounds of evidence supporting it. And after a while, we call those things, with mounds and mounds of evidence, what do we call those things? Supporting it. A particular hypothesis. You know what? You said it before.
Theory.
A theory, exactly. So a theory is simply a hypothesis has been supported by many experiments. Can you see over there? Sorry, I will move those by tomorrow. I just didn't get those out of the way. I'll move in fourth period. I think I have fourth period off today. I'm not sure about that. I know. I'm looking at your faces. You say, "What are you talking about?" You tell me science isn't, can't prove things right. Absolutely, that's what I'm saying. You can only support that theory with more and more evidence, but a theory continues to be tested with new experiments and may be proven, may be modified or replaced or proven wrong. I gotta move it. And we've seen that in the past so many times. It's amazing people don't understand it today. It's amazing people still want to think that everything you're learning in this textbook right now is never going to get changed. That's nonsense. Anybody with half a brain knows that the theories you're learning right now will be changed. If history is any indication, it will be changed. Okay? Now, I'm going to come back to these in a little bit after you do your little demonstration. What time is this period over? What time? 25? Okay, we're good. Let me pause the camera here.